Jim, shall I close this? Okay. All right, so then let's get going. We're going to cover a number of topics, as I mentioned yesterday. Going to continue with the slides that Olivier put together. There should be a link now on Boyana's webpage to these slides. Otherwise, you will find them also on the X10 website. So we'll continue and go through a whole bunch of smallish programs and then cover the global load balancing, the GLB library, and what it does for a number of applications. And that'll take us to, and maybe we'll be able to do a little bit on clocks, and that'll take us to tomorrow when we'll get back to the resilience and elasticity aspects of X10. Okay, so arrays. Mentioned this yesterday quickly because multi-dimensional arrays are central in parallel computing. X10 supports them out of the box, distinguishes between Java-style one-dimensional zero-based arrays. Those are called rails, and rails have a dense index set, so it goes from 0 to n-1. And it distinguishes that from X10 arrays, which you have to explicitly import through the X10.array package. These arrays are also, in X10, arrays are fixed size data structures, maybe multi-dimensional. These are zero-based. There used to be a much more general version of arrays that was not zero-based. And it's a dense rectangular arrays of a given base type. And implementations are provided for row major 1, 2, and 3D arrays. The code is written in X10. So we followed the obvious point of trying to write as much of the runtime and the core libraries in X10 as we could. That forces us to have a really robust basic implementation, and also gives us a check on the expressiveness of the language and so on. The Rail implementation is native. But on top of that, arrays are built on top of Rails, and they are built using plain X10. And then there's a distributed version of arrays. So as we were talking yesterday, you want to have a notion of very, very large arrays that are split up across multiple places. And so distributed arrays, dist arrays are just like arrays, but they are implemented through portions of them living on multiple places. And this is where we need to use place local handle. We will be going a lot more into detail on place local handle today. Here's a simple example that shows you, in fact, what I should be able to do is to show you the code. So let's get to, yep, so this is what the code looks like. There is a method which takes a reduce method that takes an array as argument of any given type T. Now, interestingly, so you see how simple design decisions have a lot of consequence throughout the language. So I mentioned yesterday that X10 does not have primitive types. Instead, we have structs, and users can define their own structs. Well, a nice thing about pointer-based types, such as the ones in Java, is that there is a representation for sort of a null object, an object that is very special for that type and usually stands to mean I am really not an object, I'm a placeholder for an object. Similarly, in the context of structs versus objects in X10, structs don't have such a default representation that is structurally built into the type. For pointer-based types, there is a null pointer, so that's built into the types. So X10 provides in the type system checks for a generic type parameter here, T, whether it is a reference or not, and that's a T is ref predicate. And similarly, it provides a predicate to check if the type T has a 0. So that's the notion of a default value for that type. And if it has a type, if it has a 0, then there is provided a generic class called 0, which in fact can be used to extract the representation of the 0 value for that type T. So this allows you to write generic code, which here we are assuming, and in fact right there you get, that's the idiom for getting a value of type T that is the 0 of that type. Now the reduction idiom is this is a sequential reduction idiom. It's very easy to state. You assume a reduction operator. So this is the type for a function that takes 2 t's as an argument and returns a t. You take that as an argument and then you sequentially iterate through the values in A, and you can use a V in A idiom to do that and apply this function and return the result. That's what you will get out of, that's what you get from this little piece of code. Now to run the program from the top level, you must provide a value for main. And it's a static method, public static method. Just as in Java, it takes an argument, a command line parameters that are passed in. It's a rail of string. Now you allocate a new local array, 2-dimensional array, just as we had, and n is declared statically here. So just as you would create a new array of any given, of any other dimensionality here of an array of type 2. So now you see that X10 supports also type inference. Oh, I'm in your way. So it supports type inference. Here you can simply declare a variable of type A. A val says this variable will not be mutated later, and the type of this variable is inferred from this initializing expression. And I'll have more to say about that shortly. Then you want to go ahead and initialize that variable, the locations in that variable, and you can iterate through a nested loop. There are many other idioms for iteration as well. A nested loop that goes through and assigns a particular value for this. And now you can reduce by just calling that static method and by passing in this literal, function literal, where again, you do not have to supply the type of the result that gets inferred from the type of this argument. And plus is, so I'll quickly mention this as well, X10 also has overloaded operators. So user-defined overloaded operators, so the user can define both what it means to apply a value of a given type. You do an application by taking the value and adding an open parent and a closed parent and supplying the arguments in the middle. So you get to define what happens when you do an application as well as when you do an assignment to a value of that type. Then you may choose to define arithmetic operations like plus and so on complex, for instance. So here, this is the plus operation on double. And if it's not defined, you will get a compiler error. And I'll show you examples of compiler errors. So for something like this, this has no compilation error. So you're seeing no red marks. This is X10 DT. I'm running in Eclipse. And then, as usual, you can go run a program like this by, interesting, I don't have this pre-done, so that's okay. Run it as an X10 application. And there you go. And that will return for you the value of the sum, and you can figure it out. This is actually the right answer. Okay, any questions on this? Yeah.
So normally, zeroth element is associated with the operator and the type.
No, the zero, that is correct. But in X10, the type has a 0 element. As I said, the idea behind what we are calling 0 is simply it's a default value of that type. So independent of the operation you might apply. You are correct. We could have chosen to instead consider the operation and then the 0 value for that operation. But here it's a 0 value for the type, not the operation. Right, so then you would need to pass in a constant. You would not be able to use this code for a product, and you can't anyway because, well, that's right, you are passing in the reduce operation here. You would simply have to pass in another value. You call it unit of type t as an extra argument, right? Good, that's a good question. Any other question? All right, let's go on. That is not it. What happened to, there it is. Okay, so now let's talk a little bit about the stuff that you saw on in the type system there. That thing that said t in curly for a method, curly bracket t is ref, close bracket, that's a type constraint. So X10 has a pretty rich notion of constraint types, and the basic idea is the following. And these are user-defined constraints, constraint types. In any class or struct that the user defines, certain fields can be marked as property fields. And then these property fields are allowed to occur in types. They have a runtime representation, so you can access them from normal code as usual to get their value. But in particular, you can use them in type expressions, and I'll show you now how. And these type expressions are by default checked at compile time. So the compiler has to do a little bit of constraint solving in order to figure out whether some expression involving fields, these properties on variables that occur in the code, whether they satisfy certain other condition. The compiler has to do that without knowing what the runtime value is going to be. So it has to prove this condition for all possible runtime values that variable could take. So that's why this is called constraint-based type checking. So constraints are Boolean expressions over properties and constants. We had originally grand ambitions for what this constraint solver could do, and then essentially we ran out of resources to devote to that particular project. In particular, it was clear how you can, it is clear conceptually, in practice there are still a number of design issues, it's clear conceptually how you can make this constraint-based type system be constraint generic. That means you want the user to be able to specify operations that can occur within a constraint expression, and in particular what the interpretation of those operations should be. So you might take a constraint solver as is used in formal methods for checking properties of programs, and integrate that constraint solver into the static constraint solver for X10 and the compiler. So in principle, we wanted to be able to do that. We never got around to actually implementing all the pieces to do that. But what we did do was implement a very simple constraint solver, which it turns out is undecidable because there is an open recursion going on here. So let me just quickly describe what I'm talking about. Let's see if I can put up some examples while I am doing this. Yeah, let's keep this example up there. Okay, so constraint expressions are of the kind. So first of all, you've got some terms. The terms will, of course, be program variables, and these have to be final variables. So these have to be vals. You're not allowed to have mutable variables in a type expression, because then the meaning of that expression is going to be heap dependent, and you will need a lot deeper analysis to do to get a bound on the possible values of this variable for all possible heaps. So the variables that can occur in constraint expressions are either properties, which are final variables, or other final variables, local variables, variables in the final fields in the values of local variables that are final. So those sorts of variables are allowed here. And then in particular, the expressions that are allowed are x equals y, x not equals y, and then conjunctions thereof. Okay? So in reality, that's it. You get equality and disequality over these sorts of expressions. Let me, before I describe the complexity of type checking for this, let me just go through and show you where such types can occur. So such types can occur wherever types occur. Now, X10, like Java, has these types occurring in a lot of places in the code. Wherever there's a variable, the variable must have a static type. So there is a type for it. Every method's arguments, variables, they have types. The return, if the variable is returning a value, that has a type. Constructors, interestingly, in Java, a constructor never has a type. You're defining a constructor in a particular class. That is the default value of the return type of the constructor, because the constructor should have a return type because you're returning a value. But of course here, you could be creating values of a very specific constraint type in the body of this constructor. So the return type of this constructor, you can explicitly specify, or it could be inferred for you. So that's the other big thing going on. These types occur in a lot of places. That can be quite onerous for the user. So we support type inference. So in many places you can omit these types because the system will infer these types, and in an X10 DT you hover over that place, you will see that inferred type. Now, so let's walk through and see what these types are. So I'm declaring here a vector of some generic type T. And I am requiring of this generic type that it has to have a 0. And additionally, I have declared somewhere else. So X10 has interfaces like Java does. So it uses f-bounded polymorphism in describing the signatures that a particular type variable here T must have. And arithmetic gives you the usual sorts of operations, including, of course, operators like plus and minus and so on. So T must have all of those things defined. It must have a 0. And then you declare the properties of that user-defined class in a list of parameters right after the name of the class in the class definition. So here, size is a property. You declare the property right there. So size is a property and it's of type long itself. Okay, now, internal to this class is a local instance variable that's of type rel T, and now you can see what kinds of constraints you can specify on this field. You can require that the value that is put in this field, raw, has to be non-null, and that is provided through this constraint self not equals null. So in a constraint like this, self refers to the value that is being constrained, the implicit value that this type is describing. A type is a set of values. So self ranges over all the values of that type. And this is saying that none of the values in this type is null. Okay? So self is not null, and further it is saying that the size of this rail is in fact the size of the object that this belongs to. That's what self.size equals this.size is saying. So this is enforcing that when you are going to go create a vector, you are going to have to initialize this vector with, right there. You're going to have to initialize this vector with a rail which is of the same size, and if it is not, you're going to get a compile time error. So here is the definition of the constructor for this. The constructor takes size as an argument, so at runtime this can be any value whatsoever. Compile time, you simply know that it's a variable that's of type long. You declare that this is the property through this special initialization construct called property. And then now you can initialize the fields of the local variable, the fields of this object that you are creating using a construct like this. If you were to do this before initializing property of size, you would get an error because the compiler would not be able to determine whether this constraint in raw, this condition holds or not, since it does not have at that point any information about this.size. So it's this invocation of property size that statically tells the type checker that this dot size is equal to size, and hence this constraint is satisfied and can go on and continue. Any question on this? Okay, then now it's clear what you want to do. You want to have an add operation that must check for the two vectors being added, the current vector this and the argument vector. They must have the same size. So you check that with a method guard, which is checking here that this vector t satisfies the property, and you can name arguments by default in argument lists like this are values. You don't have to write val. If you want this to be mutable, you have to write a var here, and then you cannot use that name in this type. But now this is a val, so you can. So this is specifying that the size of this guy has to be the same as the size of the current object on which this method is being defined. And in particular, it returns another vector of type t whose size is also the same as the size of the current object. And that is clearly satisfied by this. So this is okay. And then in the body, you iterate over this stuff and you assign whatever you want to do. So this is how you would define an add. And now here, you try to do something like this and you will get a compilation error. So let's see if we do. And this is, let me check quickly. I was fooling around with it this morning. What configurations? This is vector in, that's not so good. Okay. And we will check arguments, communication, class. Nothing here. Okay, so let us do. So hovering over the values of these variables gets you the inferred type. So the inferred type of W is it's a vector that takes an int as argument, and that's specified in the declaration. So that's nothing surprising, but also pulls out from the vectors declaration that the size of this vector that's in here is 5, and in fact, given that constructors return non-null values, it also infers that self is not equal to null. And now I'll get this, and let's try to run this and run as, and we do this. And I'll get a dynamic check exception because this by default X10 does not check these types statically. You can set a flag to set this statically, then it would check it. So at runtime it says, dudes, this was supposed to be true and it is not true, so you get this error. Okay, let us, interesting. Let us go back to this, and you will see here that you have to compile with static checks in order to get this to be done statically. Otherwise, you get this kind of exception that we got. Okay, so a few things to remember. There are no mutable static fields. But of course, this is computer science. So you work around that with one level of indirection. So you can put in a cell object and you mutate the values of the cell object. The default integral type is long. So this, we debated long and hard about this. It's an obvious gotcha for most people. 5 is an int, right? Well, no, it's a long. And ints are not long, ints are different types. So 0 is going to be 0 L. And so if you want it to be 0n, then you have to actually say 0n to get 0. Coercions exist other than for equals and not equals. So this is okay for less than, but this is not okay. This will be a long, this will be an int, and you can't do that, so you'll get a type error here, not a failure of equality. There is no root object. Again, this was a decision that we debated for a very long time, and in fact, initially we had a root object, and then when we introduced structs, it's not at all clear that there is some kind of object that both a struct inherits from and a class object inherits from. So we got rid of that, but we do have the notion that structs can implement interfaces. And so there is a root interface called an any that everything implements, and any has a few methods that therefore must be implemented by every struct and every class. And any declares these sorts of methods: type name equals hash code, toString, and so on. Now, type inference sometimes can surprise you. So when you're working with the language, you have to be aware of things like this. So def f7 will return a very concrete type for f. That is long with the value 7, because it's going to infer that from the initialization expression. And in something like this, what you're doing is, if you did not have this array declaration, colon array long, then the type of A would be array sub 2. Array sub 2 of long. But because you are now explicitly coercing this to be of type array long, so therefore here you will not get this to type check, because of course a two-dimensional accessor is not defined on array. It's defined on array sub 2. So there is no such method, and you'll get a type error. So you have to be careful about what happens when you use these types. Okay, so that's it for type checking. Any questions?
So in a couple of slides earlier, you said size is a property of the
Yes.
So if I specify that static check will true, the flag, compiler flag,
Yes.
would it get rid of all the things related to size and make that object even smaller?
No, as I said, properties, we made that decision that properties are runtime visible, so they will exist. We've talked sometimes of ghost properties, which are only available at compile time. But in the end, we decided not to do it because it was going to complicate the language too much.
But then I don't understand the difference between property and
Yes.
like object.
So it's a philosophical distinction. The distinction is that property fields are supposed to be part of the type of objects that can be created on this particular class or struct, right? There may be other val fields that are incidentally val, and so not supposed to be part of the type. So that's why properties are used to distinguish them, and they have special type checking that you do. As I said, the properties have to be initialized first, because the class may have fields which are actually referencing these properties. So you have to have a separate invocation for property initialization, and then you go ahead and do the type checking. Okay? All right, so now let's go on to talk. Let me finish describing the problem of type checking in the language. So, the type system, as I described, doesn't even know about arithmetic. Okay, it just knows about equalities and disequalities. So how complicated can type checking actually be? I've already given you the answer. The question is, why is it undecidable? So the proposition is that type checking in X10 program may never terminate because type checking is undecidable. And type checking an X10 program means checking all the types that occur in all of these places. So how could this possibly be a problem? Any thoughts? Aren't you guys doing types in this course? Oregon? Come on. I saw somebody talking types before I came in yesterday. Yes? So that may be the case with generic types. I don't know the answer. So for this, ignore genericity. So this is undecidable even without generics. Go ahead, please.
I don't think this is the Java, we have this thing called the serialization.
Sure.
That way it's a type system.
So let's see. So that's going in a very different direction. Now I can't remember whether we have a problem with the breaking of the type system because of serialization and deserialization in X10. We do allow the user to specify a deserializer and a serializer, just as in Java. But I'm not sure about whether a type system correctness problem is introduced by that. Regardless, this has to do with type checking for programs without any serialization or deserialization. You had another.
Oftentimes these constraint language inequalities are complete, right, to solve. So is the inequality the problem?
Not really. So the big problem is open recursion. So I am defining classes like this, and those classes are their parameters, the properties in classes, the fields of classes, refer to other types. Those other types similarly may have properties. Those properties may have constraint types. These may interrefer with each other. So effectively, there is no way to stop that recursion. To check this type, I've got to check that type, then I've got to check this type on something else, and I can keep going because of recursion in the type definition, the class definition relation. So in the cycles in the class definition relation. With that insight, now you can go construct an example that reduce some standard. And in fact, I have a JIRA that should still be open. Initially, I thought it was decidable, so I tried to work it out. And then I opened a JIRA on the X10 website. They should still be open, which actually describes how you reduce a word problem to a type checking problem for X10. So for those interested in type systems, please take a look at that. Come on. Okay, so now let's go on. Let's go on and talk about, so this stuff we've already talked about, so I'll just summarize quickly. Async creates another activity, a task that is going to execute S. Async itself returns immediately. S can reference values that are in scope. Values include val declarations in the enclosing scope, and interestingly, X10 allows for delayed initialization, asynchronous delayed initialization. So let me see. I may not have an example at hand. Let me quickly describe the idiom. So I could do something like val x of some type t, not provide that declaration, and then in here, in that finish block, I can go ahead and do a whole bunch of computation, eventually setting x equal to something, and then from this point onwards, X10 considers that this value is initialized and readable. Before that, it is not readable, but it can be initialized. Okay? And this is obviously of significant use when you got a big initialization computation to be done, and you want to do it in parallel. And tasks, this came up yesterday, you cannot name a task, and that implies you cannot cancel a task. So Java went down the path of threads which have names, and then you can do things like from outside try to cancel a thread. This was in the initial versions of Java, and then they realized how bad an idea that was because you get race conditions galore, and then it's been deprecated, and I don't understand now what the current, I don't know what the current status of X10 of Java is around that. Now, here is another important point which I did not mention yesterday about finish. I told you it's a dual to async. It's going to execute S, then wait until all transitively spawned tasks terminate. And then, and this was an interesting aha for us when it happened. Okay, so Java has exceptions, as you all know, and it has threads. And they interact in a really bad way. So what happens when some code is throwing an exception? And it's a code that is running, on some stack in some thread. So it will unwind the stack, and now it's hit the top frame of the stack, and there was no catcher. What happens then? Do you guys know? No? Well, you could probably arrange so that that happens, but that's not the default. Anybody else? It's something bizarre because there's no natural place in the X10 phenomenology to put in a piece of code to handle that situation. So in fact, I believe many years ago, at least this was the case, that there's a thread group. The thread belongs to a thread group. On the thread group, you can specify this handler that must be executed. And again, that handler can be executed by many threads who have exceptions coming up. And that's a problem. So it's not a satisfactory decision at all. Here, we have finish. So all asyncs are spawned within the scope of some finish. If an async is spawned at the top level in the body of a main, well, there's an implicit finish that catches that. Okay? So finish is a natural point to collect all these exceptions. So that's what we do. Now, of course, when you collect these exceptions, there's no order in which you're collecting these exceptions. It's a multi-set. You collect, so this is the so-called rooted exception model. Every activity, that graph of activities, spawning activities, there is a root, the finish, that collects this stuff, and then it throws that exception, but only after all the activities have terminated inside that finish. So once it is finished, it sees, is it a normal finish? Is it an exceptional finish? Exceptional, it throws that exception. Is that clear? Very good. Now, this is actually quite interesting. You could imagine that if you're doing this, and this is another X10 Jira that is open, why not have asynchronous handlers? So on a finish, instead of having only one there's no handler. It's just going to rethrow this bundled up exception. I could have a finish block with exception handlers defined, and those exception handlers get triggered whenever an exception arises from one of the contained asyncs. Then you execute the body in, let's just say, another async. And of course, you have to solve the problem of what happens when that throws an exception, but that's a standard problem. So you could do that, and we toyed with that. We essentially ended up not implementing it just because we were out of time. We had other things to do. But if you are interested in experimenting with language design in this space, that's a very interesting direction to go. It leads to certain kinds of reactive programs which can be written in a pretty attractive way. So anyway, yes? Please, go ahead.
So can you maybe contrast these constructs with, say, async wait in C# or
I can't because I don't know how they are defined, I'm sorry to say. But tell me a little bit more about them, then I might be able to say something. Async, what did you say the other?
Async await.
Await. Okay. So these things came after we did this, so I'm not quite following. When we did this design, we checked whatever everyone else was doing, and nobody had anything like this. So so what does await do?
I'm also not very, I won't be able to explain it.
I think that async will return the future.
Yeah. Fine. You can always do that, right? So I mentioned this very beginning, right? Async, there's nothing returned. It doesn't have a handle. You get to write your code to create a handle and return that handle, like a future if you choose to. And future is a library in X10. You can write your own. And then you can implement latches and all kinds of forces and so on. Very straightforward things to do, right? But that's not primitive in the language. This stuff is, okay?
So what does the fact that these are doing?
I mentioned this yesterday, let me repeat. There is no guarantee that an async at runtime is going to exist as a separate thread of activity. The compiler may get rid of it. Multiple asyncs may get serialized in some order as long as it's not going to introduce spurious deadlocks. That's allowed. Right? So there's no guarantee. This is a sign by the user saying this can proceed in parallel. It doesn't mean that it will actually proceed in parallel.
But it's the same features, right?
If you're going to create a future and you got a handle on that darn guy, you've got something that it's not going to be a separate activity, but there is a reference and you will have to execute that in that order. You'll have to force this thing that will cause other things to happen and so on, right? So you're going to have to count all these futures. They exist in your heap. There's no such counting necessarily for asyncs. Okay. So this is a point of design. And others, Habanero, I think Vivek Sarkar's team went in a different way. They took futures as basic instead of the sort of things we did. And right now, I cannot tell you one way or the other what is, yeah, there is no, so async in principle, there is no need for heap allocation. There's no requirement that there be some structure allocated on the heap when you're executing an async. But when you execute, whatever, these finishes and these promises, then there is such a requirement. Okay? Now, this point about the finish being a natural place in which to collect, and so the point is this static scope here. Finish is statically scoped. That static scoping actually is of great value when you're reasoning about the may happens in parallel relationship. And in fact, I will not have time to go into this, but I will refer you to our polyhedral X10 paper. So again, the website has all of these papers. X10 community papers, publications using X10. There is a whole ton of them. And these are by many authors. And you search for polyhedral, there is a paper, I think 2010-13, something like this. This was in fact done by, it's a collaboration with Paul Futrauer, who did the polyhedral stuff in the late 70s, early 80s, and a couple of other colleagues. And there we discovered for programs without recursion, but with for loops, async finish, at can be thrown in as well. And atomic is not a problem at all. We discovered a static characterization of the happens before relation, which is couched in terms of the path from the root to a node. So you simply, mark, if there's a finish, you mark that node as an F. If there's an async as an A, so you get a string, FA, FA, whatever. And now you take two such strings from the same root and ask, is this activity, the code in there, possibly happening in parallel with this other activity? And you simply have to look at those static paths and do a simple computation on them, and you have an answer. So that kind of static characterization is the advantage you do get when you are not refining your concurrency structure within the language primitively. Okay, now this is another advantage, which is that because you have, what did I do now? Okay, because you have this natural collection point, you can actually do a very simple kind of a map reduce. So what's a map reduce? You've got some data structure, and you want to run some computation on, let's say, each element in the data structure, producing some value. And then you want to reduce those values. Okay, so we already have an async spawning framework for doing many things in parallel. Good? So what is required? And the finish is the natural place to collect the results from these asyncs. So all that is required is an offer method. So an offer operation, any async can execute an offer with a value of type, with a value of some given type t. And that offer is, think about it like this, there's a reducer sitting in the sky at the finish. And that reducer, user supplies that code. These offers are all floating up into that reducer, and given some way in which they arrive, some serialization order, the reducer reduces these. They don't even have to be going all the way up to the location. You can look at the way in which this branching tree structure was set up for these asyncs, and you can accumulate them as you go up that tree structure. So this is used fairly frequently. I have a bunch of code examples that show that. So that collecting finish can combine finish with reduction over values offered by the subtasks. Here, the happens before may happen. This I will leave you to work out. It's a pretty straightforward once you understand how finish and async work and method calls. Unlike Silk, there is a procedure call. There's no implicit boundary for finish in a procedure call. So you can invoke a method call, and that can leave a whole bunch of asyncs behind, and the method call returns. Those asyncs are still executing. So therefore, this happens before, may happen in parallel relation. You can write down the conditions for it, and the test that I was mentioning a while ago, you can actually use that test to figure out what is going on with these things. This I am going to skip. This is simply an illustration of values can be captured by asyncs but not vars. This I have discussed before. The only thing that I have not discussed before is that this condition when CS, and this is common in other implementations of conditional critical regions, there's no guarantee that when CS will execute. If C is a condition, that only sporadically holds. It holds, doesn't hold, holds, it oscillates. Then there's no guarantee that when CS will actually execute. In fact, this is probably a good time for me to talk about guarantees around fairness. There are no fairness guarantees in life or in X10. Your code is going to run on many threads, and there is there's an expectation that if you wish to progress all your activities, all your asyncs, then you've got to periodically, wherever you've got some loop that is heavily compute intensive, you've got to periodically release that thread to go work on other stuff using something called a probe method. So you are responsible for ensuring that no activity really completely starves in the system. And the short answer for why we did this is anything else is just extremely hard. You either get into extremely specific properties which reduce the flexibility of your runtime, or into such abstract things that it's very hard to reason about with them, so we decided to punt on that problem. C itself should be non-blocking. It's a big problem. So C generally is an expression, and that expression should not have side effects, should not block. It should be checking for the values of some collection of variables. So sequential, local, pure. So none of these things are allowed within C. And the variables that are actually checked within C, those variables must be set using an atomic. Or a when is implicit in atomic. So that enables the runtime to put in code that says if a variable is being set that potentially something is waiting on, let me go check if that condition is satisfied, and you can go execute that. Obvious examples, a latch is private variable. It is initially false. Someone can release it by setting it to true, by invoking the release method. It can be released multiple times, but once it is released, then there's no further effects of subsequent releases. And then you await for the latch to be finished, to be latched, and that is a when be with nothing in the body. So you're simply checking whether this variable is true, right? A buffer is obvious piece of code. Again, conditional critical regions are actually pretty powerful, even with all of these restrictions that we have imposed. So here's a buffer for a variable type of instances of classes which must have a 0, and you initialize it to null. You can do that because it's an isref. You check that the value that you're sending is not a null. That's a method restriction. When there is no value here, then you put in this value, and the receiver suspends until there's a non-null value, produces it, and sets it, and keeps going. So that's a pretty conventional idiom for doing this. And similarly, atomic can have multiple assignments within it. So atomic and when are implemented in a per place lock. So that is why they're not particularly useful for practical programming. You can implement your own, and we have provided a whole bunch of lock implementations. So you can do something like your own scoped atomic and when on your own collection of activities, and we have code in the standard libraries that shows you how you can do that sort of thing. Then, of course, there are implementations of atomic machine operations for updating integers and so on. We have not integrated with STMs. All right, that brings me to clocks. So I mentioned last time the SPMD style of computation implicitly uses a barrier. So again, SPMD, you've got many processes running, each on their portion of some data structure. They want to execute some piece of code and then wait until everyone else in this group of asyncs, group of activities, has reached that place. And once everyone has, now you progress. So that's a barrier. And you can repeatedly invoke that barrier within the same thread. So you will repeatedly suspend until everyone else has reached that barrier. So X10, we designed a somewhat more general dynamic version of barriers. So the idea is this, we call this a clock. You can, and there is built-in support in the syntax for clock. There are anonymous clocks and there are named clocks. Let's work through the anonymous clocks first. So a clocked finish is implicitly creating this data structure called a clock. So there is actually a standard library implementation of a clock. That's, this is the name of that class with a capital C. And an instance of that is created. And in the body of a clocked finish, you can have asyncs that are not registered with the barrier. But if you want to register an async with a barrier, then you have to do a clocked async invocation. So here, you are running 4 asyncs, and they're all clocked, so they're registered on this implicit clock that was introduced by the clocked finish. Clock gives you this operation of an advance all. So when an activity comes to this point, invokes advance all, at this point, it's going to block until all other activities that are registered on this implicit clock have similarly entered an advance all method call. Is that clear? Once they do, then all get released. Yes?
How is that different from barrier?
No, it's not. Insofar as I've described it, it's not different from a barrier, except that it's dynamic. An async can finish. And then automatically the count associated with that thing is decremented, and you'll wait only for the live asyncs, not for the dead asyncs, right? And furthermore, you can spawn more. So an async can further in its body spawn another async, then that is not registered. It can spawn a clocked async, then it is. But an async cannot spawn a clocked async. Only a clocked async can spawn a clocked async. Okay? So what is crucial about this design, the way we did it, is that clocked operations are determinate. Even in the presence of this kind of dynamic propagation that I've talked about, there are no race conditions. And that is essentially coming about because of a kind of a small ownership type. You can only do clocked operation as an activity by spawning things if you are yourself clocked and you are not suspended. Clearly, if you are inside this, you are suspended, you cannot do anything. So you cannot invoke anything at all. Now, there is also a named version of it which lets you treat this clock as a data structure, and it lives in the heap, and now you can pass around this C to various guys, and in particular, you can invoke an advance just on this guy, that's a C.advance, and you can explicitly drop. So here, a clocked async termination does an implicit drop. There is no method available to drop it. But here you can explicitly drop this thing. Another big deal, I should have mentioned this, it was sort of obvious, but let me be clear. Any program written using finish async at atomic is deadlock free. There's no way that you can wait on a condition. When introduces the possibility of waiting on conditions. And of course, once you introduce locks as primitives, then locks introduce that possibility. Clocked programs with all of these things that I mentioned are also deadlock free. So that's a nice property that's built into the design of the language. If you're using clocks, you're using finish, you're using async, you're using at, you're using atomic, your program will not deadlock. Okay? there may still be race conditions because you got mutable locations and you got async. So without a much fancier type system or static checking, you will still have that. So you're not guaranteed that a program is determinate. There are certain conditions that you can follow, even in the presence of mutation, which are restrictive but often hold, which will guarantee determinacy as well. But in fact, there is, and this was work we did, but we never published it. There is a version of clocked final programs which will guarantee determinacy and deadlock freedom. And the basic idea is a val is allowed, you're allowed to write the value of a val only once. But if the variable, instead of being a final variable, is a clocked final, you're allowed to write its value once in every phase. And for clocked finals, you can show that under certain conditions, you will get deadlock freedom and determinacy. If the only mutable locations you are using in your program are clocked final, and you're using clocks, you'll still get some very nice properties. Okay, this is basically it. Let me quickly show you some examples here. And these examples are not very illustrative because they're sort of obvious, but anyway, let's do this. So what am I going to do? I have a main method. In this main method, I'm going to do an anonymous clocked finish. I want to go spawn off a bunch of asyncs, and they're all going to tell you which phase they are in. They're going to do advance all. You expect the obvious thing there. And then here is a named clock. You make that clock. And now, of course, the way that you pass that clock in to an async guy is there's a parametric version of the clocked clause on async, which lets you do that. And now you can also explicitly drop. If you drop before, if you drop and then you go ahead and do an async clock C, you will get an exception. I think you'll get a runtime exception, not a compile time exception. So let's go run this guy. And you get what you would expect. The order in which the outs are written in each phase is, there's no predicting that order. Each time you go down in that phase, you are going to, you get them all phase aligned, okay? All right. I think I've covered clocks. There is, in fact, another interesting thing that happened with clocks. And right. So what happened, and I do not recall the details now. So we did this paper on polyhedral X10. So again, what is polyhedral stuff? So how many of you are familiar with polyhedral techniques for compilation of parallel programs or sequential programs? Aha, clearly you're not from Europe, or from France for that matter, right? So a lot of my colleagues in France, Futurauer was the grandfather of this polyhedral analysis, and now, in fact, there is some very nice work that just came out from Facebook where they have implemented a deep learning compilation stack using this polyhedral libraries to get significant performance improvements. Okay, so the idea is basically this. You've got maybe even sequential code with for loops in it and arrays. And those array references are you're reading and writing various array locations. Now, if you impose this restriction on the expressions that are used to index these array elements, and these restrictions are the so-called polyhedral restrictions, then it turns out you can kind of do a pretty sophisticated compile time analysis of the read-write relationship between these variables, even though you've got for loops. And that allows you to reschedule these reads and writes in ways to significantly improve performance, particularly on modern architectures. And so polyhedral analysis is now a pretty standard part of how you speed up particularly high performance computation. What we did in this first paper with Futurauer and Tomofumi Yuki and a professor from University of Colorado was that we showed that this polyhedral theory applies even in the case where you extend the sequential language to include these async finish and act constructs. So you actually have an explicitly parallel language, but now you can merge, you can do the analysis of what happens before and what happens in parallel using the trick that I had mentioned earlier at compile time, and go ahead and complete your polyhedral analysis, and so produce schedules for execution of this code that respect finish and async, but can be much more efficient in terms of usage of your cache and your memory and so on. However, if you introduce clocks, then that analysis sort of goes out the window, in the sense that even though, as I said, clocks are still determinate, but the complexity of determining the happens, that goes undecidable. And this is really, again, because of the fact that you've got these clocks which have these indices that can range, that are unbounded, how many phases you can have in a clock, and you can get pretty interesting constraints that you can impose on what is running in parallel with what, using these clocks, that basically you cannot analyze in a simple way. So that was very surprising. We thought clocks would be a simple extension, but it turned out they were not, from the viewpoint of compile time analysis. Okay, let's go on to, right, so now here's a simple program, sequential Monty Pi. Yes, so what does Monty Pi do? Okay, so this is a Monte Carlo implementation, very bad one, very bad technique for estimating the value of pi. You may have seen this before. It's a very stupid idea. You take a square and you throw darts at a square, and then you count the fraction that land inside a circle, the unit circle inscribed in that unit square. That fraction is an estimate of pi. Okay, so very easy to implement. Just a random number, you generate numbers, and you do these darts, and you look at the x, y coordinates. You generate the values for x and y. You look at those coordinates, check if they are within the circle, and you got your fraction. Okay, so obviously this is pretty straightforward here. You find out n from your command line, and here I am showing you how you can use collecting finish. So this is an example of a collecting finish. You parameterize the finish with a reducer. In this case, it's a sum reducer for double. And in here you calculate, you go to all these different places. So by the way, finish as a control block, within it, asyncs, you can do ats, as I said. So you're spawning your asyncs all over the place structure, and that's permitted. So therefore, also, when you are doing collecting finish, those asyncs in other places can do an offer and will flow through multiple places back to where this collecting finish is. So here, do a for loop across all the places available to you, go to them, asynchronously run locally the piece of code that you need to run in order to throw that many darts in that thread. You compute your result, and you just offer your result. Okay? That's it. When all of these activities are finished, they've all done their offering, the finish guy has done the reduction, and the result is available in result. Now you go ahead and you can print out, that's the value of pi. You see how it works? Okay, so so I guess another meta point is this. Finish is really a big deal. It's a big deal from the viewpoint of the simplicity that it introduces in the semantics, and also a big deal in that its implementation is really complicated. This is distributed termination detection, which there have been algorithms going back to Dijkstra and Scholten in the mid-80s for distributed termination detection, and it is a big problem in the case of failures in a distributed setting. And we have to tackle that problem when we do finish in the context of X10. But once you've gone to all of this effort to implement a very powerful mechanism, it's good to exploit it for all the things that you could do based on top of it. And what you could do is make that finish data structure in the implementation carry user-defined values. So that's MapReduce for you. So that's what's going on with a MapReduce computation inside X10. Any question on this? this should give me an error actually, because it is asking for an n. Oh, unless I have already supplied an n. This is not nice. It is not actually responding to me. So give me a second and let me kill it and restart. Okay. Yeah, and what is it doing? So by the way, when you run this, you have to specify here the argument was 50, so that's nothing. Why is Monty Python an argument 50? Well, that doesn't matter. The important point is you have to specify the number of places, and there are no places, so by default you run in place 1. And let's do this, X10 n places, and let's do 4, and close, and in fact let's write here okay, so this is going to tell you the number of places, and it's going to give me this approximation that it built out. All right, sequential does the sequential version of it. There's nothing fancy here, just one thread running through doing this computation. You can do this in many ways. I guess this I've already shown you, so I seem to have 2 copies of this code, so this is not interesting. This is the collecting finish version. Then there is a parallel version where you use an atomic to update the same async finish, but you don't have to do this across many places, single place, and because it's a single place, so you can have a single variable where you're accumulating the result, and you can use an atomic to update that result. And again, when you're reading it here, you're guaranteed because the finish that they've all terminated. Okay. Let me go back. I want to make sure I finish place local handle, but let's see what else we have going, and then we'll get to that. So this is the sequential version. There's a parallel version with an atomic that you just saw. Collecting finish, you've seen this. And I think I'm going to skip this. We've done the distribution. So we've talked about places, we've talked about at. We'll get to resilience tomorrow. Yeah, so hello whole world, so this should be obvious. I should have done this the very first thing, but anyway, let's run it now, hello whole world. Yep, so a finish, you go to all the places. All the places in your current system, place.places gives you that as a place sequence. So let's see, what is the type of this guy? It's a place, and what is this? A place group, sorry. You get a place group abstraction, and you iterate over them all. You go there, you print out something silly like this, and now again they'll print out in some order. And I had said Belgium was going to win. So anyway, that's that. And what else do we have? hello whole world. This we had mentioned yesterday, and in fact, let me quickly go over this. Objects live in a single place. This is important. Therefore, what is critical is that there needs to be a mechanism to refer to objects globally. From anywhere, you can refer to this object. That is done by introducing a global ref. You take a value in the local heap and wrap it in a global ref, which is a struct in a global ref constructor that returns a value here, which now you can pass to other places. And the important point about a global ref is that when you are at the home of the global ref, and that is a value available in global ref, you can ask for that. So when you go to that place, you can actually get the contained value by invoking a ref on empty arguments. And you can also use that directly instead of home. You can use directly the ref, the shorthand syntax. And you can try to do a dynamic cast, which will ensure that ref is local, and it'll throw an exception if, in fact, that place cast does not work. At cannot refer to local variables, but local values. This is basically if you have declared a variable and then you have an at, then the body of that at cannot refer to that variable, because you have to imagine that when that at is spawned, all the values that the body is accessing are copied. And the variable has a value that can change. So you don't want to, we could have allowed it, take the current value, but we chose to mark that as an error, force the user to say val and copy that variable value into some place, and vals can be copied freely. Okay, let's look at place local handle. So let me, in fact, show you code for place local handle, and then I should stop. We go till 15 past, right? 20 past. Okay. Okay, so let me show you place local handle. This is slightly tricky. So let's get this working. Okay, so here's what I had said yesterday about place local handle, and let me repeat. A global ref takes a local object and produces a handle for it that can be freely serialized across places. So when you go to another place through an at, you can refer to this global ref, and at that place, that guy now has this pointer to this object here. He can send it around, do whatever he wants, and in particular, when it comes back, you deref, you get that object, you are done. So this is the way in which you pass references around across the whole thing. But sometimes you want a data structure which is such that it's not global, but it's what we call place local. That means that when you create this data structure, this handle will refer to an object in this place, and when this handle goes somewhere else, it will refer to an object at that place, which is different from this original object. And which object it refers to, you decide when you create this place local handle. So here you go. This is the place local handle. In fact, let me show you this first. It's local variable, val e. I create a place local handle with a cell. A cell is the usual thing. You can read its value, you can set its value. It's a cell of long. And when you create a place local handle, you must specify a place group, which in this case is the default place group, which is all the places in the computation. Specify place group, and you specify an initializer. So here your initializer is going to initialize it with -1. I could have chosen, as I do here, to initialize with any expression that could refer to the current place. So here, obviously, refers to the current place. It's an indexical operation, constant. So here .id in place 1 will be 1, place 2 will be 2, and so on and so forth. This is how you initialize place local handle. Now that you have this E, you can go to different places and you can dereference and get the local object. So this is a cell that corresponds to this place local handle, and you can change its value to be something like this. Okay? And so ignore the C for time being. So you do that for the E's, and then you can go now, come back out. Here you are at place 0. go back into all the different places, read the value, and so on and so forth. Now, this is how, so actually let me just run it to make sure that your notions of how place local handles work are fixed, because I'm about to throw you for a loop after that. Okay, so this is what prints out, and this is the value of E that is being printed out. So let's walk our way through it. Static is, where is static? Static is right here. So what did I do? I initially created it with value -1 everywhere. Then I set it to 2 times PID. And here I'm printing out the value here.id, so it's 0, 1, 2, 3 in the different places. Ignore this representation for now, the C's. The value that's coming out is going to be 0, 2, 4, 6. That's what we expect. Okay? It's different in each place. Good. Now, let's do the same thing, but what we're going to do is we're going to take a static variable. So here's C, and we're going to initialize it with a place local handle. And here, same expression as I had before with E, but I'm going to choose to, I mean, it doesn't matter, it's a small detail, that I choose to set its value to here.id. Okay? And now I'm going to run this code. I initialize C with 2 times PID, just as I initialized E. I run it, and with the static representation, I get the same values as with E. Here I get very different values. Any idea why I'm getting very different values? And you see that the values are, there's apparently some initialization going on that's place specific. 1 gives you -1, 2 gives you -2, 3 gives you -3. So there's a very critical point underlying this example. So I'm going to give you a little bit of, a few seconds to think about this. What could possibly be going wrong? Let me make sure that this code is visible. Problematic code. There you go. So this is the local code, and here what it does is it gets PLH is the class, it gets PLH.C, and it has a reference to that C, and it is sending that across and printing that out. Okay. All right, so the critical thing to ask is, what the heck is going on with this C? It's a static variable. Okay, in Java, you're familiar with static variables. You create one instance of a static variable for each class, right, that it is a member of. One JVM, one instance. I have got 4 places running here. What's going on with these static variables? Are they hosted at place 0? They can't be. That doesn't make sense from the language design point of view. So they've got to be hosted at every place. So that means that really every place you should think of as like a JVM. So it's initialized classes in each of these places. So in fact, there is a copy of C, of PLH.C in every place. What is this copy made of? What is it initialized with? So one answer could be you first execute place 0 code, and you will initialize it with some value, then you copy that value everywhere else. And we thought about that. We might even have had that implementation initially. But this doesn't necessarily make sense, because the class that this is a field of might get referenced for the very first time dynamically in place 2019. So why do I now need to implicitly go to place 0 and initialize this class there and then copy its state over elsewhere? Right? Remember, this is a Java-like language, so we're not going to look at all the classes that can possibly be referenced when we load our program and initialize them all. We're going to initialize dynamically. Okay. So the only real answer is that this initializer piece of code should be run when the class is to be initialized in each place. And so that accounts for the fact that now when you are executing this piece of code in C, then every class instance, place 0, 1, 2, 3, each of them is going to have its own place local handle. So there are actually 4 place local handles floating around. Whereas in this case, there's only 1 place local handle, which has a life in 4 places. Now we've got 4 place local handles, each of which has a life in 4 places. You've got 16 guys floating around. And that is the problem. Here, you are sending in this particular C, and this particular handle, when it is being referenced in, so this is the PLH that was created at place 0. It's created at place 0, you go off to place 1. The value you will have is the value that it had at place 1. What value did it have at place 1? Well, we know it was initialized at place 1 with -1. And then we executed this piece of code. But this is the static guy. This is not modifying the place 0's copy in place 1. It's modifying place 1's copy in place 1. So therefore, what you will get is the default value, which is -1, and you'll get them -1, -2, -3 in each of these places. That's what's going on. So the moral of the story is static initialization can get tricky. In this context, you've got multiple places floating around. And in particular, if you're going to work with place local handles, it's almost always a good idea to use, to initialize a local variable with that value. Then things, you don't face this problem with static initialization and things work as you expect. All right, so tomorrow we will pick up on resilience and elasticity and also deal with the formal semantics. Thank you.